Morning, guys. So today we're going to continue with our overview summary. Today we're going to look at chapter 7, which was on stoichiometry. This was the chapter that sort of brought together a lot of what we have been learning about the mole concept, all those conversions, and tried to connect them with the reaction stuff that we did previously. Let's just actually start off with that mole diagram as a summary. I'm just going to say moles of A. The mole is just a word for a box. Inside the box here contains a whole lot of particles. They do this to help us make sense of really, really tiny particles. I would be standing there forever counting individual groupings. Fortunately, they've pre-boxed them here. Anytime you look open inside a box, it was defined for carbon here. This is Avogadro's number. 1 mole is equivalent to 6.02 times 10 to the 23 particles. Again, defined for carbon, but we now borrow that Avogadro's number here for every other element. Depending on what elements or groupings are inside those boxes, the chemical here may have very different masses. So we can actually go to our periodic table, I'll say PT for short. We can look up something called our molar mass, and that would actually specify for us how many grams for this particular chemical. We had 2 bubbles when we were looking at this mole diagram here. We have a volume bubble, but specifically, there's 2 restrictions here. It had to be looking only at gases, so solids and liquids are out. But gases, turns out the gas volume depends really much on the temperature and pressure. We had to always assume we were at something called STP, our standard reference temperature, reference pressure, so that I can actually utilize this conversion here. I mentioned previous, the conversion is called molar volume. Because of our new standard pressure, instead of using 22.4, which you see a lot of answer keys and textbooks will have, slightly different standard pressure, we'll actually use 22.7 instead. So that's one of the volume bubbles here. This is the size of the balloon the gas sort of expands into. The last volume bubble we have here is volume, but specifically here for solutions, for mixtures, for powders dissolved in liquid. In this case here, it really depends on, like, this is like orange juice here. How strong did you make this orange juice? Is it really sweet, not really sweet? Is it diluted, whatnot? We would utilize C equals N over V to actually get us back to moles. Now, all of that was fine. All of that was specifically mainly on the one side, mainly for the one chemical. Now that we're talking about comparing different chemicals here on the balance equation, we can link this moles of A to, say, a moles of B. So moles of another particle, it could be reactant to reactant, it could be reactant to product, product to product, but it gives us that ability to make a prediction. That conversion there is actually the only new one in this chapter here. We can call it the mole ratio or the mole bridge, and essentially all we need is the balanced equation. We need those pesky little coefficients here to tell me what proportions these ones come in. Once you're over at moles, you're home free again. You can go back and find number. I can find mass. Note that we're now at different chemicals, so you may need to add up molar masses again. Again, similarly, we can go to volume of gases using that molar volume, or we can go volume of solutions. Okay? So that's a nice little summary of what we learned in this chapter here. It really helps predict for you, is it going to be a 2-step, 3-step, how many conversions it's going to take. In fact, as we do practice some questions here, there's 2 other little side connections. This mole ratio here from the balance equation is from the recipe. The recipe will always work for counting numbers. So it turns out, let's say I have 5 particles of A and I want to know how many particles of B. Because these are also a number ratio, there'd be no sense of converting to Avogadro, doing the mole ratio, and then undoing the Avogadro. The mole ratio will actually be the same conversion between number and number. So just note that sometimes that gives you a shortcut here. We don't quite need to go through moles if we're already talking numbers. The other little shortcut here we can do with the diagram, specifically for gases at STP, we just said the volume only really cares about what the temperature and pressure are. As long as they specify that the temperature and pressure haven't changed, you're going to find that as you do more problems here, the mole ratio is also followed by volume of gas to volume of gas. Those are just shortcuts, but primarily most of our conversions will go through mole ratio anyways. Okay, so let's just practice a question or two here. We'll start off with this balance equation here. So we have PbNO32. Let's react it with Ki. Back in our reaction section there, just given those reactants, you should be able to identify its double replacement. They're going to swap partners here. we're going to get Pb with I, potassium with nitrate. Always do yourself a favor and check whether you've written the formulas correctly here. So potassium here is a +1, nitrate here is a -1, that's fine. In general, numbers like this don't carry over. We can balance it if it's off later on. The Pb here currently is using is +2. So although lead is one of those multivalent guys, it could be +2 or +4, let's just keep lead using as +2, leaving us with PbI2. It's always good to just drop those charges there. We had made sure we worked out the ratio so that they canceled out. Once you're confident that you've written the correct formulas there, you can then add on their coefficients just to make sure every atom is accounted for, make sure mass is conserved. I noticed that this nitrate here, there's 2 of them. I only have 1 of them on this side, so I'm going to put a 2 in front. That messes up the potassiums, 2 Ks, so I'm going to put a 2 Ks here, 2 iodides, good, that matches up with the iodide there. Realistically, I probably will form some lead for iodide, but we'll just use this equation as is. Say the information we're given here, this first chemical here being a double replacement, very often it's in solution. So say I have 15 milliliters of this first chemical. The concentration of the solution here currently is 1.75 molar. I can just emphasize that this is a solution, just for simplicity. And let's say my question is interested, because stoichiometry helps us make predictions of maybe the products based on this information, maybe I want to find here how many grams of my products do I end up with. If you check your solubility chart here, although most of these guys here are aqueous, PbI2 is the one solid that forms. The word precipitate means it's a solid that crashes out of solution. That's why it makes sense for us to figure out how many grams of powder do I actually get out of this. As we look at our stoichiometry here, we realize, well, we don't have moles, but we need moles to actually compare these two here. So I need that mole bridge, moles of A to moles of B. So assuming you don't have moles just yet, we're going to do the conversion to moles. We're going to use the mole bridge over, and then we're going to figure out the number of grams. So you've already predicted this should be a 3-step conversion. Encourage you just to pause the video, give yourself a chance to try that out. As you do that here, we're looking for how many grams of PbI2. I always like starting with what's given. Now, solution problems here are a little bit trickier because I'm given 2 numbers here. Well, which number should I start off with? I always start off with the volume because this unit milliliters is a little bit easier to work with. The capital M that stands for molar actually means moles per liter. That's actually going to be a conversion factor for us. So let's just convert this volume here. So 15 milliliters divided by 1,000, 0.0150. I'm still going to keep that 0 there so that I keep my significant figures. I'm going to use my concentration to get from liters to moles. 1.75 moles for any given liter. Even though my coefficients in my recipe say for every 1 part lead nitrate, 1 part lead iodide, I'm still going to write it out here. For every 1 part PbNO32, there is 1 part PbI2. And then going from moles to grams, I would just need the molar mass of this one. I had done this previously, so for every 1 mole, you add up the mass of the lead and 2 iodides with it here. It's spot on 461, but still our periodic table at least has 1 decimal place here. I still want to put the 0.0 just to make sure it doesn't accidentally lose sig figs just because. Okay? Numbers on top you multiply, on the bottom you divide. I'm not going to worry about any times 1 or divide ones. So 0.015 times 1.75 times it by 461 gives me 12.1 grams of precipitate should form. All right? Hopefully you get that one there. Let's try one more here. The second one here is going to be a titration. Titration just basically means I react it slowly enough, carefully enough that there's no excess, there's no extra remaining. Notice in the earlier problem here, we had just made the prediction, assuming all of the lead nitrate actually goes through this reaction, we had pretended that we had extra of the potassium iodide. We have so much of it kicking around that I'm not going to run out of it, so what's limiting is the lead to nitrate. For a titration, we actually react the reactants so nicely together that there actually is no excess. We have exactly killed off one reactant with the other reactant here. Titrations here involve a reaction. Most of them are going to be acid-base titrations. So let's just try out a reaction here. Say H2SO4. We'll react it with lithium hydroxide, LiOH. Okay. Again, you should be able to predict that that's a neutralization reaction. It's acid and base. This is going to form Li2SO4. So that's going to be the ionic compound. During an acid-base neutralization, it always forms water. And then we'll just make sure we do our balancing then. Should be, because I have two H's there, I'll need two OH's to cancel it out. That should end up forming two waters for us. And that way, if you just sort of mix and match both sides, count how many you have on each side, the mass should be conserved. During a titration here, even if I sort of know an unknown molarity, it's still fair game for us to actually do the reaction to know the molarity to a greater precision. Let's say in this example here, I don't know the molarity of H2SO4. I'm going to try to find that molarity by titrating it with a certain amount of lithium hydroxide. Let's just make up a number. This would usually be in the burette. I'm just sort of dropping in the burette from one to the other here. Say I need 13.25 milliliters. The concentration of the base that I know, 0.176 molar. Just totally made that up there. We're going to use this base, send them in as little spies to actually count for us how many acid particles there are. Now the acid by itself came in by itself as a solution, so it would actually have some starting volume already. Let's say its starting volume was 10, usually just based on the pipettes I'm using here. Basically what we're going to do, start from the chemical that I know more, find moles. Let's count out how many particles are sent in. We're going to use the mole ratio from the balanced equation. We're going to figure out how many base particles kill off how many acid particles, and utilizing our initial volume of 10, trying to find for us what's the unknown molarity of H2SO4. Okay. Again, I encourage you just to pause the video, try it out for yourself. Okay. Assuming you've done that here, let's just check our work. I could totally just say question mark molarity H2SO4 just to get you used to some of the notation here. I could use that square bracket to represent concentration. I want to know what's the starting molarity, the concentration of this H2SO4. Is it 18 molar? Is it 5 molar? 0.1 molar? What is it? Okay. We're going to start off with the one that we know more. Again, given a solution here, I start off with the volume first, although I'm converting it to liters. So 0.01325, that's going to be liters. We're going to utilize concentration as a conversion factor. 0.176 moles for any given liter. Our mole ratio, our recipe says for every 2 base, it neutralizes 1 of the acid. So for every 2 LiOH, it neutralizes with 1 H2SO4. We are very used to, well, top unit cancels bottom, and all that pattern. In this case here, unlike the earlier problem, I have moles of H2SO4 up here. I actually want to keep the moles of H2SO4 for concentration. All I need to do now is I need to pick up a divide by liter. Pick up, now you know how many acid particles have been neutralized. What volume of solution was this initially swimming in to actually get it to a concentration? So here what I'm going to do is I'm going to divide it by, even though the total volume inside my Erlenmeyer after titrating would be fully diluted and things like that, we knew that the acid only came in 10, so I'm just going to write 10 in liters here. You might be wondering, well, what goes on top here? Let's just put a 1 there. That last part there just means divide by 10 milliliters. So I'm going to punch this in here, 0.01325 times 0.176. We're going to divide 2, divide 0.01, and that leaves me a concentration. We'll keep our precision here. I have 4 sig figs 3. This recipe here is exact, so it doesn't limit my precision at all. Another 4 sig figs here, so 0.117 as limited by the other one. And really coincidentally, I'm actually surprised how close that is there, but we did that molarity. That's our unknown concentration of H2SO4. So let's look at a spin-off of this question here. So this one here, and when we first saw it, it was really, really scary here. This is a limiting excess style problem. This is when potentially one of the ingredients might run out. So we want to figure out, well, which one ran out first? How does that sort of stop the production? Let's just do this by way of an example here. So let's take that Haber process, okay, really famous reaction here, using really inexpensive materials in the air, nitrogen, hydrogen, and actually forming it into ammonia. Because there's a reaction involved, we want to make sure that it's balanced. When I have an unbalanced equation, they might refer to this as a skeletal equation. It's like the skeleton of the equation there. We're going to add on the coefficients here, 1, 3, and 2. So you can double check that there. 2 n's, 2 n's. 3 times 2 make 6 H's, 2 times 3 make 6 H's. How we're going to know that this is a limiting excess question in the setup of the problem, unlike earlier, where they pretty much banked on the information for one chemical, the information for one chemical here, if I told you I went to the store and I got 10 grams of nitrogen and I got, say, 40 grams of hydrogen, now that I have amounts of both, seeing as I just totally randomly popped up these numbers here, there's a chance that one of these ends up running out first. There are multiple ways of doing this problem. Okay, let me list this problem for you here. Usually part A of this question would just be which is limiting or which is excess. Okay, which chemical was the one that ran out first? Part B, once you know what's limiting here, they'll probably ask you about the yield. The word yield just means, well, how much product do I expect to get once the first one ran out? The yield could be in many different units here. Let's just keep things simple here. I want you to find for me how many moles of ammonia produced. Again, don't get scared away by words like produce. They're just emphasizing the fact here this is on the product side. We're actually going to be able to do both of these in one step. So even if on a test it's like, here's this line and they give you a big space and then another line there, we can still do the same strategy to answer two birds with one stone. Again, if you want to just pause the video here, see if you can get a sense of, well, let's try it out. Let's see what I remember from previous. Okay. If you remember here, our strategy was actually, let's just do what we know. Let's go from the information about one ingredient, let's jump over to product, let's pretend each of them are limiting one by one. Whichever one produces less yield was the one that actually ran out first. So that's what I'm going to do here. I have the 10 and the 40. A reminder, you can't just look at these numbers and say, well, 10 is smaller than 40. This has to be limiting. Two problems with that assertion. One of them is we're measuring grams. So the molar mass of these chemicals are different. This one weighs about 28. This one only weighs about 2. So mass means something different to these chemicals. And the other thing that's not fair is the mole ratio. The mole ratio says for every 1 part N2 that I pull off, I'm actually going to react it away with 3 hydrogens. So I use up these molecules 3 times as fast as the N2 here. But in this case here, let's just do our conversions here. Let's start off with nitrogen. So how many moles of NH3 should I get if I start off with 10 grams of nitrogen? I'm pretending this is limiting. This is a conversion that I need to jump from one chemical to the other, so I have to go through mole ratio. So let's use our molar mass, and because it's diatomic, I'm going to need double that 14 on the periodic table. So 28 grams for a given mole. And my mole recipe says for every 1 part N2, I should get 2 parts NH3. I get twice as much of the ammonia that gets formed. So 10 divided by 28 times it by 2. This gives me here, give or take, 0.71. Okay? So in a perfect world, 100% yield, I have enough of the first ingredient to create 0.71 moles. Let's go to the same unit of the same chemical, but let's use the 40 instead. This is my other ingredient. So same unit would mean question mark moles, same product. In this case here, and it had one product, so it was pretty obvious. If I happen to have a reaction that has multiple products, you can jump to either one. I'm going to start off with my 40 grams of H2. Again, we mentioned here, mass means something different to hydrogen. The mass of hydrogen is just 1, also being diatomic, so I times it by 2. So this mass here is 2 grams for a given mole. I'm going to do the mole ratio here. The recipe says for every 3 parts hydrogen that I react, it reacts 2 moles of ammonia. So numbers on top you multiply, 40 times 2, divide 2, divide 3. This gives me here, I actually have enough hydrogen to make some 13 moles. Now don't be surprised if these numbers here are very off, okay? That just means that when you were shopping, you shopped way more of one ingredient, maybe it was on sale. The other one here definitely ran out first. In chemistry, if, for example, nitrogen was a very expensive chemical, we would usually do this. We'd purposely put in excess an extra amount of the other ingredient to make sure the ingredient that I bought, everything gets reacted, that it doesn't stop reacting just because the hydrogen ran out. So we've answered 2 birds with 1 stone here. We started off with no ammonia. Well, I only had enough nitrogen to make 0.71. By the time I create 0.71, this chemical runs out. That means, based on these numbers, the nitrogen is limiting, and how much got produced? 0.71 moles. So that's how you answer sort of 2 birds with 1 stone. Okay? Before I ask you to calculate how much excess is remaining here, towards the end of this chapter, we looked at percent yield. All these calculations with molar mass, with recipes, things like that, they always assume that everything is perfect. There's no errors, random or systematic. The reactions go 100%. There's no side equations. There's no impurities, things like that. If I'm told an actual yield, I know I only should get 0.71 in a perfect world. What if we were told, okay, we collect 0.40 moles of ammonia. Okay, so someone actually used these amounts here. They no doubt didn't get up to the 13 because the limiting one ran out. But you'll notice that this actual yield here is even tinier than the amount that I theoretically predicted I should have. In that case there, we can actually calculate a percent yield. So percent yield, we're going to take the actual yield. Well, I actually got 0.40. They had to give me this number. I can't predict that just from scratch. Out of the 0.71, which was already a tiny number, out of the 0.71 that I should have been able to get here, what fraction, what proportion was I able to get? So I'm going to multiply by 100 to get it to a percent. So 0.4 divided by 0.71, again, give or take a little bit of rounding here, I'm getting about 56% yield. Of the 100%, which is 0.71, which is not all that much, I only got half the yield that I expected. Now, if you were the scientist and you actually got this amount here, you'd probably try to tweak some conditions, you try to change the temperature, change the pressure, something. You try to improve this yield because we want to end up getting more bang for your buck. Okay. Last question we'll end off with here is, you guessed it here, seeing as we know which one is limiting, let's calculate how much excess hydrogen remaining. Even for this one here, there were two main ways of doing it. Okay. First way of doing it, just let me conceptualize it for you here. Seeing as I know the nitrogen is now limiting, it's good to actually start off with this 10 grams because I'm confident the entire 10 grams gets used up. Instead of jumping all the way over to moles of ammonia, what if we took the same 10 grams and we just figured out how many grams of hydrogen did the 10 grams react with? Knowing that we started with 40 here, I can just say, well, that's the amount that reacted, 40 minus that mass there. This is an extra hydrogen that got left over. Perfectly fine way of doing it. When I was in Chem 11, that's the way I learned first. The other way of doing it here, people have this idea excess is left over, excess is extra. In the way that we did part B, we actually figured out we actually had more hydrogen to make some 12 moles, 12.3 moles more ammonia. How come I couldn't make that 12 moles or so? Well, it's because the nitrogen ran out. Assuming that you bought more nitrogen, I still have enough hydrogen kicking around to end up producing the nitrogen. So what you could do, I'm going to do it this way here. Again, you can pause the video, you can try it out for yourself here. I'm going to do a subtraction between these two. I'm going to figure out how much extra ammonia should I have gotten. So 13 minus 0.71. I should have gotten some 12.3 moles of extra ammonia. That's not the excess quite yet because this is extra product that could form. I want to now know what mass of hydrogen extra left over is just waiting for more nitrogen. It wants to create 12.3. It can't make it because unfortunately the nitrogen ran out. So we've done a subtraction. We still need to calculate over to our hydrogen. So how many grams of hydrogen here? We're looking for, starting with 12.3 moles. This is extra ammonia. Let me just write down here. This could have formed. Okay. It never actually got made. Okay. It just could have been made. We'll just run the mole ratio backwards here. My mole ratio is 2 to 3 to hydrogen. So for every 2 ammonia, I would have needed 3 hydrogens to react in with it. And then I'll just use the molar mass again. Usually I put the excess unit back into the grams that they gave it to you. Of the 40 grams that I had, how much of it is left over? Let's take this number, times it by 3, and then we're going to get. We have some 36.9 grams of extra hydrogen. Remember, limiting excess here are based on this specific question, on these exact amounts that I purchased. Okay, if you then go back to the store and you buy more nitrogen, it's very possible that I can utilize some of this extra hydrogen. But as it stands, that's what we've learned. If I have information about both chemicals, there's a good chance that one of these chemicals runs out. And here's how you tackle this limiting excess style problem. Okay, so keep practicing through. Let me know if you have any questions. Thanks, guys.